Okay, let's get started, please. Let's get started, please. Okay, so we're talking about, we're in section 3.2. We're talking about the derivative. Okay, right. So somebody tell me what it means. What's the derivative? Right. Some function. Right. Here's some function. What do we mean by the derivative at some point? At some point, yeah, Sarah.
The instantaneous rate of change.
The instantaneous rate of change. Yep. Can you give me the the formal limit definition? Anyone give me that?
The f c plus h, or well, it's the limit as h goes to 0.
Okay.
F c plus h minus f of c over h.
Over h, right? And this h on the bottom is secretly c plus h minus c, right? To make it clear that what we're doing is we're taking some point c and some other point c plus h, and we're taking this thing here is the slope of the line through those two points, right? The change in the y value is going to be f of c plus h minus f of c. The change in the x value is c plus h minus c, right? Namely h. Okay. So right. So if this limit exists, we say f is differentiable at c, right? Differentiable at c, and we call f prime c. We denote this limit by f prime c and call it the derivative of f at c. Okay. Right, so that's that. Right. We also at the end of class last time we also noticed that you can write this in a different way. You can write this as f of x minus f of c over x minus c as x goes to c. Right. That's what we said at the end of last class. So instead of calling this second guy c plus h, we could just as well call that guy x and say, let's look at f of x minus f of c divided by x minus c. Differentiable at c. Okay, so we could, if we call this guy x, right? If we call this guy x, then this thing would be written f of x minus f of c, right? And this thing down, and this length here would be x minus c, right? Instead of calling it h. So it's just a matter of a different notation. Anyway, everyone all right with that? Okay. So I'm going to do something now that I'm a little bit, I have some trepidation of doing, but I'm going to do it anyway. Yes? Okay, so what does differentiable at c really mean? What does differentiable at c really mean? Okay, and I'm going to try and give you some sense of it. So, differentiable at c. Okay, what does that mean? That means that that this limit of f of x minus f of c over x minus c as x approaches c equals some number. Right? It means that there's some number, and this limit goes to that number, right? Right. That's what differentiable means, right? That there's some limit, some number at prime c, such that this happens, right? Nobody would disagree with me, I hope. Okay. So I'm going to rewrite that and see if that tells me a little bit more of what differentiability really means. Well, I'm going to move the f prime c to the left-hand side. Okay. So the x minus c. I'm going to subtract f prime c from both sides, and I'm going to combine it with this fraction. Okay, so I'm going to find a common denominator, right? The common denominator is x minus c. Right? I hope everybody sees what I did. I had a plus limit of a over b equals something, and then I just moved the d to the left-hand side and rewrote it as a minus db over b. Right? Just using elementary school fractions. Right? The db over b is the d. Okay.
What's the limit of the
Same limit. Okay. Now, let's see. Let r of x be this whole thing. Okay. Denote this whole thing by r of x. Denote the whole left side by r of x. Okay. I know what's he doing. What's he doing? You'll see in a second. Okay, let's denote the whole thing by r of x, and then I'm just going to say this is the same thing as saying that the limit of r of x is 0. Okay. Yeah, Noor.
So do we change f of x to r of x?
Nope, I'm just calling this whole thing, whole expression on the left-hand side, r of x. Okay, and I'm saying, well, then I'm just this thing just says the limit of r of x. Okay. 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 So, in other words, what we're saying is that f of x minus f of c minus f prime c x minus c equals rx x minus c, and the limit of r of x is as x goes to 0, x goes to 0, x goes to c is 0. Right? Did anyone getting lost? You may not know where I'm going, but maybe you know where we are. As long as you know where we are, that's all right. Okay. Anybody?
Yeah, I'm lost. What did you do?
All I did was said, what's r of x, right? What did I do over here? I let r of x be this whole left-hand side divided by x minus c.
Okay.
In other words, this thing is r of x
okay.
times x
Okay.
minus c.
I got it.
Okay,
Yeah.
right. Right. I multiplied both sides. Yeah. Right. This is right. The top. The numerator here is r of x times x minus c. Okay. Okay. So really, nothing has happened. Okay. But what does this say? What does this say that that f of x equals f prime c x minus c plus f of c plus rx x minus c, where the limit of r of x as x goes to c is 0. Okay, so now I'm going to do another elementary school move. These have all been sort of elementary school actions. common denominator, moving something to the other side, multiplying both sides by x minus c. I'm going to move all these. I'm going to move these guys to the other side, and see what it says. Okay. Can anyone see what this says? Can anyone translate what this says into a geometric statement? Or just any sort of statement? What does this look like? F of x, so being differentiable means that f of x is f prime c times x minus c plus f of c plus something or other. This thing that vanishes. I'll give at least, if somebody comes up with it, I'll give a point or two on the next example. Elise?
Is it the equation for a line?
It's the equation for a line. You get it. Equation for a line, right? Right here, this is the equation for a line. A line of what? Of slope what?
This, like in terms of the form or what the.
What's the slope of this line here? Here's a line. What's the slope of this line?
The slope would be the derivative of f of x.
This is the slope right here,
Yeah.
right? You've got. So let's think about what this line is. So let's call this line L of x is f prime this plus this. So suddenly appears this line. You're looking at the definition of derivative, and this line somehow turns up. Okay, we just did some arithmetic on it, and then this line shows up. What is this line? Well, let's see. What is this? What's the value of this line at time c? What is this line? So you haven't said exactly the magic word, but you've got. What is this line? The tangent line. Great. So I'll give both of you like 2 points on the next example. Okay. If I remember. Okay. Right. This is the tangent line, right? Because look, L at time c. What's its value? Well, you put in c for x, and you get f of c. Right? So here's your graph f of x. Here's your graph of f. Okay? Here's time c. This line is the line that at time c has height f of c. Right? So it passes through this point here. Right? What's the slope of the line? The slope of the line is the slope of the tangent line to f. Right? Slope of the tangent line to f. The tangent line. This guy here is actually the tangent line to f at c. To the graph of f of c. So what does being differentiable mean? What does being differentiable mean? It means that your function is basically the tangent line plus something that vanishes as r goes to c, as x goes to c, plus some sort of error that vanishes as x goes to c. So I'll write that in English. F differentiable at c means f of x is basically the tangent line at c to f at c plus something that vanishes right? This something is r of x times x minus c as x goes to c. And in fact, just to be precise, it vanishes even if you divide it by x minus c, right? Because r of x, this thing, even if I divide by x minus c, it's still going to vanish because r of x vanished. So it's like a thing that vanishes doubly fast, right? R of x vanishes, x minus c also vanishes. It has some sort of fast vanishing. Okay, so yeah, so that's basically what differentiable means. That your function is basically a line. Okay, means that at that point, your function is basically a line. Is well approximated by a line. So f of x, f is well approximated by a line at x equals c. That's what differentiable is, that you are a line like Isaac.
The derivative of a higher power polynomial
Mhm.
would still be about a square, or let's say it's like a fourth.
Sure.
fourth
So you have some polynomial.
So
Yeah.
it's a fourth. You do that.
Yeah.
It's like 3x to the third.
Yeah.
And
Yeah.
then 4x to the third.
Mhm.
Well, then it's not a line. Then it's still a derivative, right?
Right. So the derivative is not a line. Okay. What is a line? So yeah. So don't mix these two things up. The derivative is not a line, but the function is line-like, right? The function is differentiable. So here's a point 2. This function, x to the 4, is differentiable there. And what we're saying here is that this means that the function is well approximated by its tangent line. And indeed, as you look at it, if I zoom in closer and closer, right, the closer I get, the more this curve looks like a straight line. Okay, so that's the point. Okay, if you keep on zooming in, the thing looks more and more like a line. And so, so if you see something like this, you say, oh look, am I differentiable at this point? Well, look, if I zoom in here, no matter how far I zoom in, that corner never looks like a line. It always looks like a corner, no matter no matter how deep I get in. Right? It's still going to be a corner, not differentiable. Okay, right? Something like this. Even if it's got a very sharp curve, but not an angle, right? Not an angle, or not anything like this. Right? If it's something like this, I say, oh look, if I zoom in far enough, I really can't tell the difference between that thing and a line.
So absolute values aren't differentiable.
Absolute value is not differentiable here, but you see it's differentiable everywhere else, because everywhere else it's in fact is a line. Yeah.
If it's not differentiable at one point, does that make the function as a whole non-differentiable?
No, we just can't say not differentiable at that point.
Okay.
Yeah. Yeah, so it's not differentiable at that point, but it's differentiable at all of the points. Okay, so that was the hard part today. I hope you got something out of it. Okay, so but this actually leads up to something something else. So theorem f differentiable at C implies f is continuous at C. If you're differentiable at a point, then you have to be continuous at that point also. Okay, and so sort of the idea of this is, why does that make sense at this point? Well, if you're differentiable at that point, that means you're basically a line, right? And lines are predictable, right? The behavior of a line is predictable. Since the behavior of a line is predictable, your behavior is also going to be predictable. Okay, so that's sort of like your intuition about why this ought to happen, right? If you're differentiable, you're line-like. Well, you're going to be continuous. Okay, but to make this mathematically proper, here's how one argues. You say, well, if f is differentiable at C, that's the same thing as saying that the limit of f of x minus f of C as x approaches C exists. then multiply both sides by, whoops, sorry, there should have been an x minus c on the bottom here. Sorry. Multiply both sides by the limit of x minus c as x goes to c. And what you get is that sorry, I made another change. So instead of saying that it exists, let me say that it equals some number at prime c. Okay, multiply both sides by this. The limit of x minus c as x approaches c. Well, what's the limit of x minus c as x approaches c? 0, right? That's 0. So I get 0 on the right-hand side. And on the left-hand side, I get the limit of f of x minus f of c as x approaches c divided by x minus c and times x minus c. Right? Because I can combine those two limits together. Yeah, I'm sort of skipping a step. Right? I should write the limit of this times the limit of that, and then say the limit of this, the product of the limits is the limit of the products. But I'm going to skip those and just put it together so I can cross it out. Right? So that's what we get. The limit of f of x minus f of c as x approaches c is 0. Right? But what does that tell you? That the limit of f of x as x approaches c is f of c. Right? So we're continuous. This should be only a one directional arrow. That's a pretty serious mistake. So this one should be a one directional arrow, not a two directional arrow. You may think I'm crazy to obsess over the direction of the arrows, but if I had put this as a two-directional arrow, what would that mean? That would mean that being differentiable is equivalent to this, is equivalent to this, is equivalent to this, is equivalent to continuity. That would mean that differentiability and continuity are the same idea, right? In other words, if you're continuous there, then you would also be differentiable there, right? That is completely wrong, right? You know that, right? If you have a continuous function, does it have to be differentiable? No, we just saw a couple of examples, right? It's these guys are continuous, but they're not differentiable, right? So continuity backwards does not, this opposite direction is very false. Continuity doesn't imply differentiability, right? So if I had left this arrow up here, it would have been like a crime against humanity or something. Okay. Any questions about this? Okay. Okay. So one comment. This also shows you that if f is not continuous at C, then what? what does this logically give you? Differentiable at C implies continuous at C. If you're not continuous at C, then you cannot be differentiable at C, right? So, not differentiable. That's- okay. This sort of reasoning is called contraposition. Right? If A implies B, then not B implies not A. The second statement is called the contrapositive of the first. Okay, so this statement is actually equivalent to F not continuous implies F not differentiable. So I shouldn't say then, is equivalent to, is logically equivalent to the second statement. I forgot to ask. Shoot. Okay. Okay. So actually, let me just take 1 minute to ask something that I should have asked before I handed out the feedback. So, so this is sort of a strange thing to do, but I have, I take videos of the classes, right? And I've actually been doing this for like 3 or 4 years. So I actually have this class over and over. Like, there are videos of this class already in existence. They've been hiding. Basically, they've been hiding on YouTube, but what do you think would happen? Or would it be beneficial to you, or would it just cause chaos to make these available? In other words, you'd have access to the entire course, all the lectures before, right now. Would that be a good thing or a bad thing? I want to hear people's opinions. Because I can think of one bad effect. The bad effect is that I've given away everything that I'm going to say, right? And then if I come in and talk, you'll say, well, he already said it on the lecture, right? So that's true. So it could result, so it could be kind of a problem if some students watch the lectures, then those students might feel like, well, I don't need to come to class. Well, maybe that's true. Maybe you don't need to come to class unless you have questions, right? So, yeah.
If we were to put them online, would there
Yeah.
be an assumption that we watched them,
No.
or would it just be okay?
No. So this isn't, I'm not saying that we're going to switch the class to a flipped class. That would be a huge change. Certainly we could do it that way. The flipped class where everybody watches the lecture first and then comes in and works on the homework or asks questions. That's one way of running a class, and I've done it that way before. It actually can be kind of interesting because then we can talk about other subjects, right? We can sort of like, but then I don't have the chance to make sure that everybody is understanding the material. So I'd just like to hear if there's any. How about this? Send me your opinions if you have any, because I was about to do it yesterday and then I backed off, thinking that this could lead to a lot of trouble. Okay. Yeah, I should have asked you before you wrote down, before you handed in your feedback. Okay. Okay. Yeah. So I mean, in some sense, it would make things convenient for students because then you could watch it at home. You don't have to come in and you don't. If you got it off the lecture, then you wouldn't have to come to lecture. It's basically you can have your lecture at whatever time is convenient to you. Although you've already arranged your schedule so that this time is convenient. So I guess that doesn't. Yeah. So. Okay. Anyway, send me any comments and I'll think about what to do. Okay. Okay. So other facts about derivatives. Other facts about derivatives. Okay. The ones that are going to be useful are the following. That one, if let's say that f and g are differentiable at c. Okay, so you have two functions and they're differentiable at a point. So, and the first thing I'm going to notice is that the derivative of some number times f at c is the same thing as that number times the derivative of the function at c. The derivative of some function at c is going to be that function times the derivative. So you can, it's again a commutation comment, right? That you can either multiply by a number first and then differentiate, or you can differentiate and then multiply by the number. So if I have 5x cubed and I want to differentiate that, that's going to be the same thing as 5 times the derivative of x cubed. Okay, so 5 times 3x squared. Okay. And the reason is the limits and arithmetic thing, right? Because this is just a statement about limits. The differentiation is just taking limits, taking a particular kind of limit. And we already know that you can interchange limits and multiplication. Okay. Number 2, the derivative of the sum at c is going to be the sum of the derivatives at c. Okay. So if I have the derivative of, say, x squared plus 5x cubed, I know that's going to be the derivative of the first guy plus the derivative of the second guy. So that's going to be 2x plus 15x squared. And the moral of these two, 1 and 2, basically give you that polynomials are easy to differentiate. Right, you just differentiate term by term. Right. Okay, somebody gives you a polynomial, you just differentiate each of the things and add them together. That's the derivative. Okay, so just to put up some examples, here's a simple one. 15. Yeah, 15x squared. So g of x is 2x plus sine x. Take 10 seconds. Right, think of the answer. What's the answer?
X plus cosine
X, what?
2
Plus cosine x, right? So the derivative, you differentiate this guy, right? This is x to the 1, right? So you get 2 times 1 x to the 0, right? 2 times 1 x to the 0 plus cosine x, right? So that's just 2 cosine x. Right. So you see what to do. You see what to do with these things, right? If you have combinations of functions, then you can pass the derivative through the numbers, and you can pass them through the pluses. Okay. Okay. Let me.
It's okay.
Let me put up a slightly trickier one, just as an example. Oops. If f of x is the square root of x, what's f prime some of you know the answer already. What's the answer?
1/2.
1/2 x to the negative 1/2. How do you know that? By the power rule. But what was the power rule based on?
Like the exponent? Well, I mean, because you know that what square root is 1/2.
Yeah, but remember how we showed the power rule? We used
Based on Pascal's
triangle, right? But where's the row in Pascal's triangle for x to the 1/2? There is no row, right? There is no row in Pascal's triangle for x to the 1/2. So actually, we don't know that. At this point, so those of you who've seen calculus before know that the power rule is going to work for any real number. But at this point, we only have it for natural numbers. Okay, Becca.
Well, you can also use the integer loss of finding using the limit of f of x.
Yeah. So that's what we'll do. So we'll just say, well, let's take the limit of this over this as x is h goes to 0. Okay. Who knows what trick we should pull at this point? Anyone familiar with this? Anyone seen this before? Okay. So the trick is you have this something square root minus something square root. You want to get rid of that, so you multiply by the sum of those roots over the same thing. Right. So you multiply by, again, a fancy looking number 1. You multiply by 1, but this 1 is chosen so that you're going to get, if this is a minus b, then you're going to get a squared minus b squared on the top. So you use the old trick of a minus b, multiply by a plus b over a plus b, and you get a squared minus b squared over a plus b. So that's the trick we're playing. We multiply by 1. Right? It's always okay to multiply by 1. Okay, so we get the limit of this thing squared minus this thing squared over h square root of x minus x plus h minus root x as h goes to 0. Okay, does it just take another second? Right? You end up with the limit of h over h x plus h plus root x as h goes to 0. And you see what happens? What happens? Well, the h's cancel off, right? And you get 1 over square root of x plus h plus the square root of x as h goes to 0, right? So you get 1 over 2 root x, which you see is the same thing as 1/2 x to the negative 1/2. And so that makes you think that maybe the power rule also holds for other numbers. And in fact, we'll see that it holds for all numbers. But not here. Okay. Okay, that's it for today.